Hello, everyone, and welcome to another episode of the Data Science Decoded podcast. We're happy to see you. The previous episode, we had audio issues, and we decided, okay, we have to solve it. So it took some time, and now hopefully all the problems will be solved. So tell us in the comments or give us just feedback if everything is well now. And I missed Mike and Nir. How are you guys?
I'm okay. I'm glad to see you again. I think the last time we recorded it was 3 weeks ago, right? And as Daniel said, it took some time, but we are using another tool for recording. So tell us what you think. I'm strengthening what Daniel said.
Perfect. And
Nir?
Nir, how are you?
Yeah, I'm doing great. I'm doing great. It's a sunny day here in Southern California.
Happy to hear. And to our viewers, today we have quite an influential paper, the paper that had the first ideas behind decision trees. And the title is Problems in the Analysis of Survey Data and a Proposal. And it's from 1963, so it's around, 60 years ago plus. And it's by James N. Morgan and John Sonquist. They're both from University of Michigan. And I'll read you the abstract. Okay, so they say, most of the problems of analyzing survey data have been reasonably well handled, except those revolving around the existence of interaction effects. Indeed, increased efficiency in handling multivariate analysis over even with non-numerical variables, so probably categorical, have been achieved by largely assuming additivity. An approach to survey data is proposed, which imposes no restrictions on interaction effects, focuses on importance in reducing predictive error, operates sequentially, and is independent of the extent of linearity in the classification or the order in which the explanatory factors are introduced. Explanatory factors is features in today's jargon.
Daniel, I have a small question. Then
Mhm.
I'm reading the second sentence. I'm not sure I fully understand it. Indeed, increased efficiency in handling multivariate analysis, even with non-numerical variables, categorical, maybe ordinal, has
Yeah,
been achieved largely by assuming additivity. So we're just doing some one hot and just adding them.
I
What is he
think
talking about
I
later?
think he prior, and that's my guess from reading the paper, prior to this paper, many of the problems that they're dealing with were solved assuming some kind of linearity of the features. So to our listeners, this is like a tabular data problem, right? So they call it survey data. So they have like some information about people, their age, gender, education level, etc., and an outcome, or like the why, what we call the why, and they try to understand what's going on. And so I hope I answered your question. Do you agree, Mike? Makes sense?
I guess I'm just thinking about translating categorical variables to some one-hot representation. Then you're just
Mm.
getting this representation. I was thinking about that. I don't know then when these one-hot encodings and all the other encodings, which are less trivial than one-hot, was invented. But maybe I don't know. Additivity is we know that additivity is very convenient assumption and in some cases it
Hmm.
solves problems.
Yeah. So the paper, and I think we all agree on that, has a really high verbosity level, right? So like many pages of the introduction and the problems, it was like reading more like a story than a paper. You agree?
Yeah, just like modern deep learning papers, you have some log likelihood formula, some auto regressive prediction for the large language model, and maybe some formula for some top k precision or recall, and except for these formulas, you have nothing, and these formulas are being repeated in almost any deep learning paper. But now, by the way, now I think it was a situation 2 years ago. Now the situation I think is worse, because now all these LLMs papers are just talking about some benchmarks. But the difference between this paper and between these LLM papers, I think they don't have many tables. Modern LLM papers having dozens of tables of different numbers or the different benchmarks. Here it is simpler.
Yeah.
Yeah,
So in a
I
sense, yes, Neil.
I was reading this and I was looking for a mistake. I thought that Daniel was breaking our ball, so to speak, and again gave us a paper to read on like general prose paper, because this paper is not well written. Okay, this is it's not well written, uncorrelated with the length of text it has presented us. It's not well written. It's hard to understand. It's really hard to understand. But
Yeah.
we will digest everything for the listeners from this paper, and serve them with just the anecdotes.
By
Yeah,
the
that's a
way,
great point.
yeah, I fully agree with Nir. And one more point: the fact that the paper is long doesn't mean that there is irrelevant information in this paper. I think we reviewed several long papers, for example, like Shannon ones and like Fisher ones, and in this paper almost nothing was irrelevant, if any. But this paper, it is very important paper, but it can be uh, instead of 25
Compressed.
pages, it can be 5 pages.
Yeah,
Yeah, it
compressed.
was published in the Journal of American Statistical Association, so it should be a really good journal. And they are economists, so maybe they're used to writing more verbose
Okay.
descriptions.
Okay.
But regarding those points, so what we plan to do, the first part, until they give their proposal of their algorithm, they raised problems in survey data up, like what was the problems that most of practitioners back in the day were facing. So there's 7 problems, and we're gonna list them and talk about them a little bit. Then we're gonna go to their solution, how they solve those problems, at least how their proposal is solving them. So I'm gonna go over the 7 problems they raised. So one is variety of information. That's point number 1, meaning there's so many different features, and it's like, in their words, it's like a big data, right? Back in the day, it was, compared to today, it's small data, but to them, it's like there's so much information in it. So that's one problem. Second, they call it classification rather than continuous variables, meaning categorical, what we call categorical features,
Yeah.
right? So, you can be income, so it's broken to high, low, medium, for example, right?
Hmm.
Etc. So it's not some number that is continuous.
By the way,
So that's
Daniel,
second. Yes.
there is important distinction between ordinal features and the categorical features, because ordinal features you can compare. For the categorical features, like cat, or dog, or horse, you just can compare it. There is no quantitative relationship between categorical features, but there is a quantitative relationship between high, low, and medium income. You can sort them in some
Hmm.
order. So I want to
That's true.
remind the readers about that.
Great point. Thank you, Mike. Number 3, measurement errors. Okay,
Daniel,
so
Daniel, can you scroll down? We can see it.
Yes.
yeah, we did first, we did second. Number 3 is here. Errors in the measurement. So what they say here, like people misreport their income or education, from different reasons. So
Hmm?
it's like part of a noisy data set.
Yeah, we call it
That's,
noise. Yeah.
yeah.
By the way, we have our these problems today as well. This is
Of
missing
course.
data, and
Yeah, yeah.
Yeah.
yeah, I've been struggling with missing data in almost any job I did in the last 8, 10 years, because the data unfortunately has a tendency to be missing.
Yeah, number
Mhm.
4 now. Okay, number 4 is sample variability. Okay, and measurement error. So in this case, they say they something that relates to Fisher back in the day. So they say when you sample from like a population. So just by definition of doing finite number of samples, you have some error attributed to it.
Yes.
Um, so this is more like from a statistical perspective. So that's number 4. Again, we'll put it under noise, I guess, still. And number 5, extremely important, but that's what they say here. But they talk about intercorrelation between the predictors. Okay, so between the features
Hmm.
of our data. What's do they mean? So people with higher education also are, they tend to be with higher income.
Hmm.
Okay, so this is like some kind of correlation between features and then how you deal with it. Okay, back in the day, it was problematic. And that's 5. 6, interaction effects. And again, I'm not sure here. Maybe you can tell me why do you think it's different? But for them, they say that the effect of education on income, for example, can be different for someone who is self-employed versus someone who's working in a corporate job. So you cannot like add features. So again, I'm not sure if it's here correlation or nonlinearity. This was a little bit again confusing. There's so much words written.
You know,
I
okay. Start talking. Okay, I'll be
okay.
a second.
When I read this paper, the additivity in my mind was I immediately took it to probability. So if you have two events that are, and you can add the probabilities of the events, it means they do not intersect, right? Otherwise,
Mm-hmm.
you have to, otherwise you have to add them both and remove the probability of intersection. And when you have a lot of probability, a lot of events that are intersecting with each other, the additivity is very complex because you have to remove all the combinations of all the intersections. And I mean, in terms of calculating the probability of oring everything, or adding up everything. That's where I went when I read this, but I don't know that that's what the author meant here for
Yeah,
sure.
again, not clear.
Here, by the way, this is a very interesting angle. I have a bit different angle. Maybe it is related. Then he's talking about interactions between features. He's talking about some kind of non-uniform sampling. Because if your features are independent, you're sampling, you tend to get some uniformly distributed features. But when your feature have some interaction, it is not the case, because there are quite small amount of people with higher education who have very small income. You just have no chance to sample that. This is the first effect. And the second effect, when you have such features, as Nir said, and they gave a very beautiful explanation, you just can edit. You just need to understand the interaction, because you can't just add p of a plus p of b without doing minus a intersection of b. And what is
Mm-hmm.
a
Yeah.
intersection of b? It is a feature interaction, the interaction between features. So it is a bit different angles, as I understand.
Yeah.
Yeah. I think that the thing that I then scroll down in the paper, and and I saw these diagrams that they, um, the intersection diagrams that they present there, and that was, I guess, what made me think about that. But you know, it's this paper is so convoluted in terms of text that that it's hard to say. It's hard to for me even to say if that's true or not. What I'm thinking.
Yeah. So let's move to the seven. The last problem or claim that they say about data is that there's the concept logical priorities. You can see it here, and chains of causation in the real world. So they're saying that some features might be coming prior to others in time. You know, let's say the education of the parents came before the education of the person that being questioned, and his income later after he gets his education, etc. So there's some kind of causal interactions, and if you get just data, you can see correlation. You don't see the causation there. So that's a really good point. As far as I can tell, whatever they propose, which is trees, decision trees, they don't deal with causality. I think what they meant, and we're gonna see it, like maybe you can by yourself, if you know a priori some causal relations between the features, then you can build a tree in that way to represent this, your prior knowledge.
Yeah.
And the other methods that they had back in the day, you couldn't do that. Okay, so that's the point. And here are the plots you were mentioning here, but we won't go into them. And let's move to their proposal. So how they want to solve those problems they've encountered with data. Okay, so I'm scrolling to the listeners. There's like around 10 or more pages of ChatGPT verbiage. And okay.
Imagine that in these days, you had to write it by yourself. It is crazy. No chat GPT, you know. All this text, the person actually sat down and wrote that. I just can't imagine it in 2024. Just can't imagine.
So I'm going to read. We now describe the process of analysis in the form of a series of decision rules and instructions. Okay, we think of the sample in the beginning as a single group. So they take the whole data as a single group. The first decision is what single division of the parent group into two will do the most good. The second decision has to be made. Which of the two groups we now has the largest remaining error sum of squares, and hence should be investigated next for possible further subdivision. Okay, so what they say here, take all of your data and try to break it into groups. We're gonna see soon exactly they tell us step by step. And the idea here is at the end, reduce the error, or right between what their model gives and the actual measurements of the outcome. Okay, and you can see here, first they say, and there's equations. They say, okay, let's take our whole data, and back in the day, there was no train test split. So they evaluate on the train, right? On meaning all of the data.
Yeah.
So they take all the measurements that they gathered, and their model at the beginning is just the mean of all of the measurements. So each measurement gets the mean of all of the data, right? And then you calculate error, the difference between the actual outcome and the mean of everything.
Yeah.
And that's the starting point of the algorithm.
Yeah.
Then the second step, they propose dividing by first choosing, like a feature, and try to divide now the whole population or the whole samples that we have into two groups on that feature. Okay, and this is equation number 3, and they call it sum of squares, or they explain sum of squares.
Yeah.
And again, they have some kind of convoluted way, at least in my opinion, to define like the error, right? I'm used to talk about errors. Okay, they say residuals, which is okay, but still there's not a lot of rigorous definitions of, at least in my opinion, right, of what they're doing.
Yeah.
And it took me time to understand
I
also
mean,
the equations.
yeah, I think the gist of it, Daniel, is that they want to find the split that reduce the sum of squares. That's how I read it.
Yeah, which is the error. So meaning
I guess it's
the sum of squares between the actual outcome
yeah.
to what the model predicts.
Yes. Yeah.
Okay, and they do it
It's like MSE but
sequentially.
without the mean. Yeah.
Okay, and do it step by step. So you break on one feature,
Yep.
you find the place where you break into two groups all of the data, then you move to another feature and try to find the best place to break. I saw at some point they say, okay, in theory, if you can break it to infinite parts, so you can like get 0 error, which is overfitting.
Yes.
So what they propose when they're gonna stop, so they say you stop when the best next break into two groups that you find reduces the error by at least 2%. If you reduce by more than 2%, sorry, by less than 2%, you stop. So they say at worst case scenario, if each split reduces 2%, then you have 50 breaks. So their tree has like 50.
That's the stopping criteria, I guess. Yeah, for them.
Yeah,
Yeah,
the stopping criteria.
Daniel, several small remarks, observations maybe. Then I remember when I read it 3 weeks ago, I was thinking about clustering, and why was I was thinking about clustering? Because
Interesting.
yeah, what they are doing here it is quite similar to hierarchical clustering. You start from one big cluster, and then you are starting to divide. You divide in two clusters, and then you take the clusters. You choose the cluster which you want to divide due to some criteria you define. There are different criteria, and then you stop at some moment. Okay, there's some stop criteria like here. So it is quite similar to I don't remember what is the name. I think it is called hierarchical clustering, maybe agglomerative. I don't remember. This is the first observation. The second observation, this stopping criteria. If our listeners are using k-means, this elbow criteria is kind of similar to this, because you want to improve your clustering, and you want to reduce your error until you see that the reduction rate became too small for each next division. So there is two things: agglomerative clustering and the elbow in the k-means.
Interesting. So from an algorithmic perspective, you say the steps of how to do it is similar to clustering, not
Yeah,
conceptually, because
yeah,
it's
yeah,
tabular data.
yeah. But the
Yeah.
clustering we don't have tags. We usually don't have tags. We have untagged data. So, but in principle, it is very similar.
Guys, am I mistaken to look at equation number 5 and say that this is not sum of squares but squares of sums?
They call it explain sum of squares, and you call
Yeah,
it
but I don't see sum of squares. I see squares of sums.
source of sum.
I think it's a
Yeah.
mistake. Yeah. They're not
But also
squaring.
here they defined sum of squares.
That's okay. Number 2,
Yeah.
it's actually okay.
Mm.
Number 2. But then they actually treat only the second term there, which is a proxy for the expected value squared, I guess. When you are estimating variances, you can estimate the second moment and then subtract the mean estimation squared. This is what they do here, in a way, I guess. But this is not sum of squared. This is a proxy for the first moment, the mean squared. What they present in 5.
I see where you're going. I just looked at it and I said, okay, this is just the error between my model and the true outcome.
This is not the error. This is actually a term they want to maximize, I think, to
But
reduce.
that's true. But they say maximizing this is minimizing the error. It's the
Yes,
same.
yes, yes, because it's a minus sign there. That's the first time I ever see this kind of approach, by the way.
Yeah, that's why I agree 100%. That's why it's also confusing to me. Again, we used to minimize error, and they just try to maximize
They call it
the
explain
oh
sum of squares, but I never heard this term.
yeah.
Yeah,
Again, to our listeners, just think about it as reducing the error between
yeah, yeah.
what the model predicts and at each split of that we do and the actual outcome that we have.
Hmm.
That's otherwise I couldn't understand why they're maximizing the opposite. But okay, again, that's 1963. Maybe they had different concepts back in the day.
Yeah, I think the rationale they have is that the variance is the e of x squared minus e squared of x, and they're trying to maximize the e squared of x to take away as much as they can from the variance. But e of x squared is also changes when you change the splits. So I'm not sure this
Oh,
is not.
interesting. Okay, didn't think about that. And let's see what's important here. Here, that's exactly what they say. They choose the group that is the largest.
Mhm, mhm.
And this is the
And
square error, by the way.
Yes. Sure.
yeah, that's how I looked at it. And now they say they talk about implementation. Okay, again, this is 1963, and they say, okay, you need to implement this with quite a basic computer. They talk about running out of storage capacity. So they did some algorithmic tricks to put some of the data in memory and optimize it so it will work better. And here we have an example, a
Hmm.
chart number 2,
Which is a
when
tree
they,
diagram.
yeah, which is an actual tree, and you start with one feature, you split it by the ethnicity, which is not so politically correct. Our
Yeah,
viewers can see it here, but again, 1963, it was okay.
Yeah.
yeah.
And then by age, that's the second split, etc. So you actually see a tree.
Hmm.
Um, as far as you can tell, what is the main difference between this algorithm and, let's say, what today we call a decision tree? What's the main difference?
I think that we don't use decision tree as a decision tree. We use it as a part of a random forest or part of boosting trees. But I think the principle of building these trees remain more or less the same. Maybe what changes some kind of regularization. So you don't just stop and then your the improvement of your error become too small. You are regularizing it by the depth of the tree, and I don't remember some quite complex regularization in XGBoost and in LightGBM, but the main principle
Mhm.
dividing in the areas in which the error is the biggest. I think this is the main point and the main achievement of this paper, and we are doing it today with some additions.
Yeah, I agree. I agree. This is in the terms of decision trees, this is indeed a seminal paper because they were the first, as far as I can tell, to actually plot the decision tree and say let's minimize or maximize a quantity to in order to split it optimally, quote unquote. And
Yeah.
and and yeah, we can use other metrics, maybe Gini or entropy, but it doesn't matter because they did it with their type of metric and it worked for them. and we still use it. I mean, even in random forest, you use the same approach, more or less, uh, with a lot of trees, right? Um,
Yeah,
Mm-hmm.
yeah, uh, but the building block is this, right?
Yeah,
Am I
yeah.
mistaken?
exactly. Yes.
Maybe we regularize or do fancy stuff with the cost function, but the underlying principle is still stays the same.
With entropy.
Yeah, with entropy, for example.
Entropy it's sometimes called mutual information.
Mention,
There are
yeah.
Yeah,
many types of regularizations.
yeah.
Yeah. I want to add that I think what's really valuable here is the explainability, right?
Mm-hmm.
Once you have this model, you can actually look and see how decisions are flowing, like how you
Mm-hmm.
move and compare. Let's say I build a model and there's a new person comes and I know of his data, so I can actually follow, okay, oh, he's not a farmer. Okay, then he's not a high school graduate. Boom, he's gonna get this amount of annual income.
Yeah,
Okay, and I can actually work with data also easily as a practitioner.
yeah.
And I guess prior to this idea, they had some kind of linear models, but mostly based on
Mm-hmm.
some more statistical approaches. And
Mm-hmm.
then I don't know how they explained it, what their explainability was. So I
Mm-hmm.
think that's another valuable perspective on this paper.
Yeah.
By the way,
And
do you guys know what is a linear tree?
I
There is
don't.
some there is some creature in machine learning, and I read about it a couple of years ago, which is called the linear tree. You are building a
Okay.
tree, but at the edge of it, if each tree, you build linear model on some of
Mm-hmm.
the features. Okay, I admitted I didn't see it too much in practice, but it's still some, some wedding between trees and linear models. And
but the total
linear models.
model is still not linear.
Yeah, it's still
Yeah, yeah,
and that's why it is called linear tree. You have
yeah,
many linear models.
yeah,
So you don't have one decision in the edge, in the leaves of your tree, but you have
Yeah.
some simple linear model of several features, of some subset of features.
yeah. Believe it or not, in my AI in signal processing, in radar signal processing course, I show how I classify between, say, a pedestrian
Hmm.
signature and a car or bicycle signature by extracting features and then using random forest. And it works very well and it gives you a perfect explainability. And that's why we like these trees algorithms, right? And
Yeah.
this is not, I mean, this is very easy to read, high school grad, not high school grad, but sometimes the features are, for me at least in my world, the features are the flatness of the spectrum, is it high or low, and so on and so forth.
Mm-hmm.
So,
Yeah.
but radar practitioners and can read this stuff, and it's very explainable. That's why I like it. Sometimes it produces even better results than SVM, in my experience, for my kind of problems.
Yeah, but by the way, one of the contributions of this paper is this trees for explainability. Now we have very complex models, and I think
Yeah,
Daniel, we've been talking about one of your ideas in our chat, but in my
Yeah.
opinion, these trees or small ensembles of trees are very good in explainability. If you have 500 trees in a random forest, it is not very explainable. But if you have, 10 trees or maybe
yeah,
5 trees, it is perfectly explainable. So we are
hmm,
currently looking, we are searching for some trees which can explain our tens of billions of
yeah,
parameters models. I don't think it can be done with some very simple tree, but still we have this very good, very powerful explainability tool in our package, and it is
Mm-hmm.
this paper.
yeah,
Yeah, I would second that. As a practitioner that works on products that goes to various users, when they always ask me, okay, we want more explainability, trees, again, or random forest, etc., are the answer. That's like the best you can do in that domain, in my opinion. Yeah, cool. So that was, again, not easy to read paper because of the prose and verbiage, but we made it through. Had a lot of impact on what we do today.
Indeed.
And I have already a few ideas for next week. So stay tuned to our audiences. And I wanted to remind to give us a like and subscribe. And I guess we're going to see you next time.
How do they
So,
say to kids these days? Sharing is caring.
Yeah. And,
and caring is fun.
Yeah.
and also listening podcasts about math and machine learning is also fun. And we are very close to very good, very round numbers of subscribers on YouTube and in Spotify. So you can try to give some push and to give us these numbers.
Thank you. Thank you, Mike. Thank you, Nir. And see you, everyone, next time.
Bye bye. See you next week. Bye.